Okay, I think we can begin. Good morning. I think that it will be helpful if we begin by going over the problem. So does anyone have a problem with the homework assignment? Because it's due tomorrow and you have to submit, I think, before midnight.
Morning, sir.
Morning.
So I just have two questions. Let me just quickly get my stuff. Uh, the one is for question 4A.
Which one is?
It's the one
I
with
don't.
the isotropic harmonic oscillator.
Right.
So you in your slides, I think it was for I just want to see what the lecture is. In your lecture slides for the time-independent perturbation theory,
Right.
you had a where you for the linear product of the y component acting upon zero, you had it as a negative for half.
Hmm.
I'm not sure how you got that because I tried to determine it, but I couldn't find it because for me it has to be zero. I'm just trying to find the precise slide where you showed that.
Let me just try and share the question because or maybe not open it directly here, but I should have the homework assignment somewhere.
Okay, thank you.
Because I might be thinking of it different or totally different because I had already started writing the memo and one student had already sent me something. Let me just check. Problems. So let me see which one is one. Four. Right. So part A or part B?
Part A, please.
Part A. So for part A, see what I got.
So I get for that the first order correction that it is zero. That part I
Zero
get.
eight. Yes.
But as soon as you go to the second order correction, you end up where you have for your bra on the top in your absolute value squared. I have a zero at the bra, then I have an x operating on nx, then a second bra of ny with a y acting upon a zero, and then the third bracket is zero acting upon zero, which that third part would just be one. But the
One. Right.
zero acting or the x acting upon nx is just one of the hints that you gave us,
Oh,
which
I see. So I realized this with one of the, I think it was Kevin. What you have to do is that the X has to act on the zero.
so
So
the x has to act on the zero, so it has to be flipped around. So it has to be nx um, x zero and
not
zero
not
y n zero.
not necessarily flipped around because you are working in a complex vector space. So
Yeah.
the minute, so you know that a let's say that the hint that I gave you was that a dagger acting on n. Right, this should have given you, I think I wrote it as root n plus 1, acting
Yes.
on plus 1. This
Yes.
equation you can flip around or take the dagger of that equation. So you end up at once it acts on n, then a dagger will just give you an a. Then that this will give you um, n plus 1 square rooted with n plus 1. So you end up with say there was an x acting on 0 and x, so I'm saying that it has to act there, right? So you write this as a plus a dagger acting on 0. So for example, from what I wrote there, so a acting
Yes.
on not 0, so this will not give you 0, it will give you, I think, just um,
It would just give you a one. There will only
yes,
be a state of one.
1 acting on an x, right? And then this
Yes.
other one, is 0 because it's the flipped version of a acting on n. A acting on 0 is 0 because there is no state which is below. If you think of it in terms of ladder operators, there has to be some lowest rung that you cannot really say this might be the floor. You cannot go below the floor. So once it acts on the lowest state, it cannot go further. So it's to give you
Yes.
0. And then this operator, once you flip around, you get that 0, or acting on a dagger has to be 0. So
Yeah.
this one, once it acts there, then it automatically vanishes. So the only one that would be left would be what I wrote there, just the state 1 with an x. And similarly, if you do, you get 1 with an y. And these are just delta functions. So you get delta 1 and x, delta 1 and y, and the other one I think it's 0, 0 and whatever you call the other thing. So these are the delta functions that you get. But there obviously
But
will
the
be
thing
some
is, sorry, sir, but the thing is with those delta functions, the only way they can be one is for
yeah,
nx and ny to be one. But then you end up with a problem inside of your summation where you have your nx minus ny both times with h bar over omega.
mm,
That forms part of your second order equation that you have. Then you're going to end up with zero as your denominator.
think so. You might have this must not equals to say 0, 0, 0, and you're left with no. There are different ones, I think. So um, what did I get? So your problem is that you got that part, right? But the problem was that you had this en minus e. So
Yeah,
this
so at the
might be
bottom,
0,
because
0.
if I look at what you did
Look,
in your
look, you have this, you were separated from this ground state, right? So the other, you just got that just to be 1, 1, and 0. Go and calculate the energy for 1, 1, 0. It's just h bar omega 1 plus 1 plus 0 plus I think 3 over 2. And then you take this energy, which is the energy of
okay,
E1, 1, 0, and then you subtract the energy, which would be the 3 over 2, h bar omega over 3. So they are not going to give you 0 minus 0.
okay,
They are
I will
not the
do that.
same. Okay.
Okay, thank you, sir. And
Mm,
then the last question I have is for where is it? Is for 3B.
right.
I'm
Okay.
not sure how to do it because if you apply the or not definition, but for your angular momentum, we have that Lz is equals to h bar times m, where m is your magnetic
Correct.
quantum number. How do
Correct.
you then do, or how do you act that upon your bras and kets?
So Lz acting on L comma M, this would have given you just h bar, but this is now a C number. It's just a pure, which is just the
Yeah,
eigenvalue comma m. This is how it
y-
acts.
yeah. So, but how do you go from that? I understand how to get to that part, but I'm unsure because if you now have your bra and you have for your m's being three different values, and you create a 2 by 2
Um,
matrix.
no. So for there, I just wanted you to check. So I would have just assumed that the state with zero was the one that was non-degenerate, right? So that's the one that I would have gone and applied those formulas, and all of them you just get 0 and 0. That's what I just wanted you to check.
Okay,
The
so
the
that
problem
both the first order and second order corrections will be 0.
was 0 because the state that you can apply non-degenerate perturbation theory, that M there was 0.
Yeah.
So that automatically gives you a 0. My point was that I was thinking that the eigen values were going to be expanded in terms of this lambda, but I think Kevin pointed out to me that he's just getting a lambda. So it's not like he's getting in one of the questions where maybe you might get 4 plus lambda squared, and then you have to try to expand that. Here it was already order 1, order lambda exact. So I think that question was slightly badly phrased. So if you can just set up the problem for, and I can see that you do understand this type of operations, then you should be getting your marks there.
Okay, no problem. Thank you, sir.
Right, because that was my fault. I should have. You see, my problem was that the original problem I think had a different sign, and I changed that sign, and that ended up changing the entire problem. So it ended up being badly phrased. Any other questions? So we can begin. Right. Someone said something about degenerate perturbation theory, but I'm not sure. Degenerate case. So when you have a degenerate, so you remember this. So there are two cases that you have to consider. You first have to check whether your energy levels are. So there are two cases. So there's the case where, which is the one that you're struggling with. For the degenerate case, what you have to do is that the first thing that you have to do is that you have to form these matrix elements, H alpha beta, which will be depending on how you label them. So I think in one of the slides, I just called them. So this is the degenerate case. You have to set up these things, right? So you have to give me a case, whether it was question 4 or 3. Is they're, yes, they're still here. Okay, let me just go ahead and think of a case. So let's say that I gave you the for B. Okay, so for 4B, you have to compute these things, right? And just see what I wrote in my mind. Right. I think in one of the lectures last week, I tried how to get these ones right. So is everyone happy with these ones? Okay, maybe I should repeat them. So these states, right? I'm doing this. I think the degenerate state was 100. The other one was 010 and 000. So you 001. Then in order for you to form these matrices, so if you look there, this might be H11, H12, H13. The one sitting here, let's start maybe with H3, H31, H32, and H33. The first thing you have to do is that you have to form this matrix, and I label this vector. So I call this vector 1 head, this vector 2 head, and this other. You can call them A, B, C, or whatever. So if you wanted H33, you have vector 0, 0, 1. Then your perturbation was x, y. And let's say this vector 1, you look at which vector is the first one. So it's this one. So you have to find what these things are. Are you fine with that notation? Okay. And then how does this type of operations act? So this vector here is labeling x, this one is labeling y. I think today's lecture might be too very long because we still have to explain the things, right? So this then simplifies into 0, x, 1, 0, y, 0. This is correct. It wouldn't really matter. And then, which is this, there is no z operator acting anywhere. So it will then just hit this one, 1, 0. And what is this? The eigenfunctions, the unperturbed, so you get 0. Similarly, for the other one, if I had chosen 3 and 2, let me just change the color. So if it was, say, if you wanted H32, you look which one is 2, it's 0, 1, 0. So here it will be 0, 1, 0. So, but it doesn't matter. That's the reason why I would have, clever student would probably have tried the third row, because you can see that most of these vectors will be orthonormal. So even the second one, again, it's going to have a 1 there and a 0. So it will give you the same thing there. It's just that the difference now will be that 1 there, but it doesn't matter because this again is 0. So you get another 0. The one that I didn't do, and this matrix, if by now it's symmetric, so you already know what those two are. So the only one that I didn't do last week was this one. And that one I think is 3, 3. So you get 0, 0, 1, x, y, 0, is this 0 and 1, right? This is 3, 3, h3, 3. And again, now what I did last week was that we're going to get 1 and 1 on the z vector, but I just assumed that everyone then will be able to compute what 0, x, 0, and 0, y, 0 will be. These vectors I showed in one of the lectures that the diagonal elements n, x, n, these are what? I think this is the third time I'm doing, or fourth time. Yeah, 0. So there. So the only elements that you then are left to calculate will be 2 by 2 matrix. And by now, it's like I calculated this 2 by 2 matrix in the lecture, because this problem is the same problem, right? Just that I've added a new dimension. So because you are struggling with degenerate case, let's try H11, which I also showed you last week. So H11, you take this vector, it's the first vector, so it's 1, 0, 0, because this is the first vector. And then you have x, y, right? 1, 0, 0. This then simplifies to 1, x, 1. Don't have to do anything. This is 0 again because of this condition here, which it's shown in one of the lectures. So again, 0. Now you will calculate that other one, and that other one, right? So let's say, which by now you know what this matrix will be. But once you've calculated, the first thing then you do is that you diagonalize this matrix, right? So I've shown you how to obtain these matrix elements. You form this matrix H from that matrix H, but let me just clear everything. You just diagonalize. With the whiteboard. Share. Right. Let's say that maybe you got some matrix with 0, 0, 0, 0, 0. It's let's say, I don't want to give the correct one. Maybe, let's say 1, 1, 0, 0. This is not correct. Then you just find what the eigenvalues of this matrix will be. And those, say you find that maybe they are plus or minus square root 3, the other one maybe square root 2. Once you have this, then you know what the corrections to your energy will be. So maybe the first energy might have been 3 over 2 h power. You just add these eigenvalues. So it might be that this is the correction to the lambda, whatever parameter that I used, and you do the same thing, 3 over 2 h bar omega plus square root 2. Let's say I was expanding, okay, I think in the lecture I was calling them alpha, so you have to call this either E. They are just eigenvalues that you obtained. So this is how you obtain the correction to the energy levels. Then the correction to the wave function, what you do is you know that it's going to be some linear combination of the unperturbed stuff. And these numbers you get by, once you diagonalize this matrix, you can read off what are your eigenvalues. So maybe one might be 1, 0, 0, 1. And by your labeling, this is what I called 1. This is 2 head, 3 head, and this might be 4 head. So this thing here, you just read off what that number will be. So it's 1 over square root 2, 1 over square root 2 of 1 head vector. And this 1 head vector was 1, 0, 0. Right. The second vector is 0. You're reading it from there. So it's just 0, 2 plus 0, 3 third vector plus 1 over square root 2 of the fourth vector. Maybe there was no fourth vector, but maybe it was 0, 0, 1. Right. So 1 over square root 2, 0, 0, 1. Then this will be the correction to your state. That's how you handle degenerate case. And then, are there any other questions? Let me just check in the chat. Then let's say question 1. I realize that some of you might not be familiar with the Dirac delta function, but it's defined such that if you integrate across all your space, the contribution only, so say there's dx, and we've already used this function for hyperfine splitting. So if maybe there was delta x minus a of f of let's say x, right? This entire contribution to this integral is only coming from one point, x equals to a, right? And contributes always to that point, f of a. And leaves down. So if there are no other questions, I think we can lecture them. So if there are no other questions, right? Okay, then I think you should submit. I mean, the memos already have done in terms of being written. So we continue with the application of the variational principle. So the variational principle, you know that your ground state just gets some trial wave function, and then you compute this. This thing will be an upper bound. So we want, I think the last time we applied this to the helium atom. So today we will be doing it for this H2 plus ion. So it will consist, say you have some proton, they will be separated at a distance. You can call this capital R. This will be easy, but it's just repetition of slightly different but similar integrals to what we did last week for helium atom. So the only other thing that you will have will be the electron. Say this distance, you can call that distance, they call that R, the other one to be R prime, right? So if let's just say that the total energy of the system will be given by the kinetic energies pi squared over 2mi, and then you have to usually you have to sum over all the particles, but I will by now know what might happen. And let's see, there's only one electron, so this term vi minus rj for this ion will not be there. Now this contribution, the protons won't contribute. Why? So I'm just saying that the only contribution once you do this canonical transformation that P is given by H bar over I grad, the only contribution that will be coming, you only get one Laplacian minus 2 come from the electron, and you have del squared. And I'm asking why isn't there 1 over MP? Obviously, because the mass of the proton is nearly 2,000 times bigger. So the contribution coming from the nabla form, or basically you're just saying that the electron is the one that is busy moving. These things do not carry any kinetic energy, so they don't contribute because their mass is much larger than the mass of the electron. And then you have plus, so this will give you, let's see, it's minus because you are multiplying these two. So you get minus e squared over 4 pi epsilon 0, 1 over r, plus 1 over r prime. Right? So this is your Hamiltonian for that ion. Now, let's say that this distance there, or this part of the proton was moved very far, maybe to infinity, or maybe you're just saying that capital R might be bigger in comparison to the Bohr radius. So you will probably only be left with this part of the system, and this part of the system we've already solved, right? This is just the standard hydrogen atom. So you might guess that your trial wave function has to be that of hydrogen. So it's just psi naught, and this other one would be somewhere at infinity. So you just get that this, your first guess for the trial wave function would be just go ahead and use the trial wave function for hydrogen, which let's say you know by now is given by square root pi a cubed e to the minus r over a naught. This might be correct, but you can go ahead and try to use this trial wave function. But we are not treating this entire system in a symmetric manner. So the best trial wave function would be the one that will be symmetric in terms of that r and that r. So you have to try and symmetrize. So it will just be some normalization, psi, say 0 of r plus psi 0 of r prime. So this is the trial wave function that you're going to try and use. Right. So using this variational method, what is the first thing that we have to do? Right. You always have to first determine the normalization constant. So let's go ahead and do that. clear everything. Right. So you know that let's write this. So you know that 1 has to be integral d3r of psi squared, right? And then this thing is called LCAO. It's just linear combination of your atomic orbitals. So we took the two linear combination, or we symmetrize them. So this will give you a squared integral d3r psi 0r squared plus psi 0 squared r prime. But there's going to be these two psi 0 r prime, psi 0 r d3r. The original atomic orbitals were already normalized, right? So this will just give you a there's an integral there, so you just get a squared, write everything out. Now this integral, for now, just denote it by I, and that's where the real work will start. So you end up with that a squared 2 1 plus this integral that I've called I. So other name for this integral is the overlap. So it's the inner product between psi r and psi of r. So we then have to try and compute what that integral will be. That's clear. Maybe I should just go directly to the slides and use those ones. Obviously, when I write on top of the slides, it's going to be slightly messy, but at least then I can explain the formulas much better. Let's go back, right, and explain or try to get this. So is everyone happy with this, right? This part. This is just kinetic, the electron. The only which is more moving is the electron distribution from P and the only other step is 1 over R. You make this type of modular type of computation that orbiting the proton, which is being directed at.
Here is some information for what is the significance of Valentine's Day.
Sorry, so you broke up for like the past 30 seconds, half a minute there.
Okay, let's change the network and use another one. So, okay. Okay, so I think before I broke off, can everyone hear me? Okay, okay, fine. So I was saying that our guess for most of these types of computations will be our first guess then will just be you just go ahead and use the normal hydrogenic wave function. However, what this is doing is treating the first proton quite differently from the other proton. So you had to try and symmetrize so that your wave function, which I'm using the wrong notation, will just be a linear combination. So you take the one from this proton R, but you also add the other proton, which is right, which is this other one, R prime. Then the first thing that you have to do with this type of computation will be to try and find what that normalization constant is. Right. So this is what I did on white. And what did I say these integrals were? One. Because the original atomic hydrogenic atom orbitals or wave functions were normalized. So you end up with that this just gives you a squared of, I did this previously, 1 plus I. So in order for you to find this thing, you have then to compute what this overlap integral will be. So you have to find what is psi naught r prime with psi naught r, which is what I will be doing in the next slides. As I said, but so you're going to choose your Cartesian system such that this axis runs along your protons. So proton 1 and proton 2 will be along the z direction. Right. And then your other electron might be located at some other distance. It's the same system that we were using last week. Only difference is that now these are there because the protons are fixed. It's not really moving. So let's this you call that r prime. The other one is r. Then you just use the normal cosine rule. So this will give you square root r squared plus r squared minus 2r r cos theta. And then you put this into your radial wave function. Now, the only part that you have to evaluate will be this one, e to the minus r over a d3 prime. Right? And you just take this and you plug it there. So this integral, this is the integral that we want, e to the minus r prime, where r prime is given by this thing. So the repetition of what we were doing last week. So you call this integral u, or in this case they called it y, right? So you end up with just integral e to the minus y over a. If you do your u substitution, this part there, differentiate whatever is inside there, this becomes some form of du, right? And everyone is happy as to how to do these integrals. I think last week I called them e to the minus beta x, x to the n, right? So everyone happy as to how you go about doing the type of integrals, which are what would be sitting there. We did this last week, right? Or should I revise as to how you go about doing these integrals? Please. Yeah, actually, I realized, yeah, it's just, let me see. So maybe I should not use x. So let's say that you will end up with integrals of the form e to the minus beta r to the n, maybe going from a to b. So the way that you do this type of integrals is that last week I defined something called I0. I0 is just the integral from a to b, e to the minus beta r. Just that last week I was calling rx, but it's the same, it's a dummy variable, it doesn't really matter. Is everyone happy that this should give you minus beta e to the minus beta a minus, let's say, beta b e to the minus beta a, right? And then once you have this integral, then how do you get the other one, which has the r to the n? Let's see if people played it next week. It's like we did this even last year, you differentiate with respect to beta. So to get the other integrals, so I gave you this. This is the last formula that was appearing in one of the last slide of the last lecture. So to get other integrals, all you do is that you differentiate with respect to beta n times of I0. And I had given you what I think I gave you I1 and also I2. So you're going to just repeat the same procedure I did last week. You get those integrals that I gave you, you plug them into that expression, and you should make sure that you get this right. Now, this then it's again what I called I theta. This means that, remember that D3R is given by R, there's some part d theta and d phi. This gives you 2 pi. This is what we've been doing for the past maybe 5-10 minutes. So whatever you get here, you still have to integrate over R. And that integral will give you, this is the final integral. Right. Again, you can see that you're doing the same type of integrals because you have things like a to b, r, n, e to the minus beta r dr, right? And then just make use of those integrals. I give you these tables. I think you only need I0, I1, and I just differentiate them, plug them into this type of formulas, and then you find what this overlap integral will be. So then you can solve what is the integration, the normalization constant, right? Then, because you remember that you want to find what is h, which is just the overlap h psi. It might be better just look at what is h psi, and remember that the Hamiltonian is given by h bar to m d squared plus there's going to be this 1 over r plus 1 over r prime. And then just check what happens, right? So this psi is 0, right? It's going to act, and it's a function of r, the other one a function of r prime. It's going to act there on that 1 over r, and it's going to act there, right? So so maybe I write everything down, minus 2m delta 1 squared plus 1 over r acting on psi 0. You get a similar term, but this will just be dummy, say psi 1, which is this one, right? So once you take that expectation value, you just get, it's just going to give you that E1. But there will be extra terms, and the extra terms are what you are going to be labeling as exchange, because there will be certain integrals where you are multiplying that psi r, but it's not hitting that 1 over r, it's hitting this 1 over r prime. So you end up with integrals of the form psi of r on 1 over r prime psi of r, which are these integrals. And again, you have to repeat the same long process of trying to find what these integrals d, and the other one, which is called the exchange, this one. Maybe I should just sketch as to how you go to compute these things. Maybe I should leave it because of time. Let me just check if I've gone. There's still time. So I'm going to try and compute this d. So x I tried, and it's not even, which will just repetition of what we did last week. Should I try and compute d, or should you will be fine doing it yourself? Okay, maybe I'll give it as an exercise, but point is that what you notice is that these parameters are depending on this r over a. So just change notation and maybe call r over a to be your x. Then once you put everything there in terms of this exchange para and the direct integrals, you end up with this function and try and plot this function. And what you find is that there will be some parts of your thing where the energy is below or becomes negative. It becomes less than the total energy for a free neutral atom and one proton. So there is some state where your system then becomes a bound state, and then you can, by just using that function, also check that where does this minimum occur. You can find that, and also these things, and you can compare them with what you get from experimental data. So then the next one that we will be looking at will be the hydrogen molecule. And this one I think is much more involved. So again, you're going to have two protons. Right? There's going to be what you're going to call electron 1, and then another electron, which you can label electron, the second electron. So these are your protons. These are your protons. Let me just. Where is it? So I've labeled this again. You repeat the same thing. This, the distance between the two protons, you label that as r. Actually, I shouldn't have drawn that because it's already here, right? So this is what you first have to write the Hamiltonian for. So let's see. So your H, remember that the only kinetic parts are coming from the electrons, right? The protons are immobile, so they do not move. So you end up with H will be given by minus h bar squared over 2m. Laplacian first electron plus delta 2 squared, right? Plus, let's see, there's going to be, let's start with the positive one. So there's going to be this contribution. So this gives you plus e squared over 4 pi epsilon 0, 1 over, let's see, 1 over that r. This is this contribution. The other one, it's negative electron, negative electron. So again, that gives you a plus. So you end up with plus 1 over R12, right? And let's see, this 2, right, will give you a negative contribution. So you get minus 1 over R1 minus 1 over R1 prime, right? And we still have to consider these R2s. So this is positive, negative. So again, you get minus 1 over R2 minus 1 over R2 prime, right? So this is the Schrodinger equation that you will have to try and solve, but we're just going to use the variational principle to guess what the trial wave function will be. So again, you guess something that will be depending on product, but then you'll have to try and symmetrize that product. So if I went ahead and do that, see, it's this one, right? But you've symmetrized it. However, you don't really know whether this sign there will be plus or minus. And remember that your full wave function, right, it has some contribution coming from the spin. So if you were to choose, because fermions in general have to be, let's see, people are still here. Fermions have to be symmetric or antisymmetric under interchange of variables. They have to be so this means that if you were to choose one which I'm saying that the plus one is symmetric, the wave function coming from the spin part has to be unsymmetric. Similarly, once you've chosen something that is being antisymmetric here, it will mean that this has to be symmetric, so that overall wave function of your system, which is made of the spatial wave function, which is what I wrote there, and these guys, the total has to be antisymmetric, and these chi's going to be, you've seen this, right? So if I give you 1, 1, the other one might be 1, 0, 1. You did this forms a triplet state, right? And it's what I did last week. You want to change bases from this JM into J1, M1, tensor product, J1, J2, M2. You calculate the Krebs quadrant, that thing that we did last week, but you can check the triplet state, right? It's symmetric, so it's that this one might be 1 over square root 2. By this, I just mean up, I mean the state you saw last week. It's the state half, tensor product, half. These states will give you something like that 1, 1, or one of those two. This half. It's what we did for the Zeeman effect. So you do a change of bases, but my point is that these triplet states will be symmetric, and then there will be the 0, 0, which you can check is given by 1 over 2 up, down, minus, let's say this, right? So it depends if you were to choose, okay, let me say this, say if you were to choose this one to be antisymmetric as your trial wave function, then this one has to go with the triplet. And then if you had chosen this to be symmetric, then this will then have to go see, maybe with the other one. But for now, we're not just going to be worrying about that. For now, we are just going to try and find what those normalization constants are. So again, you're going to repeat the same thing that we did. You said that 1 has to be equals to, and then you square everything. The original wave functions, atomic ones, are already normalized. So you only get that thing that you called I, and which we call compute. Right. Now you again have to try and find what is the expectation value of H. So the first thing that you have to do is check what happens when H acts on psi and minus. You manipulate stuff, you're going to start getting things that will be depending on 1 over R1, multiplying maybe an R1 prime, multiplying an R2. And then once you've done that, then you sandwich the other vector, plus, minus. See, just taking inner product. So the inner product of that Laplacian will give you the E1. It's similar to what we were doing for the ion, but there will again be these integrals which you call exchange or direct, right? And then if you want to write them in terms of those things, I think maybe I give this as an exercise. See, but for this problem, remember that there are 2 electrons here, so you also have to consider VE, which is the one that will, that term which is R minus R1 minus R2 mod. Try to compute those integrals, write them in terms of this D2 and X2s. Again, then you will find this function, because these functions are given in terms of X, which I think I called R over A. You can plot this thing, and you get for the plus or minus, you get that for one of them it's unstable. So whereas for the other one it does have a minimum, and you can form a stable bound state. Whereas for the other one, the minimum will be occurring at infinity. So this one will be unstable, the other one will be stable. And can also find this J, which is just the difference between the energy of the singlet and also the triplet. And this might be what you get. So I think in terms of exercises, all I can do is maybe ask you to compute these things. I think we can take a break. It's just maybe I wanted to go through this example, but I think yeah, I think maybe we can stop because I've been talking for too long. I think maybe the WKB lecture, I might record something shorter. Okay, stop recording.